Okay. Welcome everybody. Today we have talk by Juan Alday. Allow me to read. Él estudió ingeniería de las energías en la Universidad Politécnica de Madrid y se introdujo en el campo de las ciencias planetarias durante el máster en el KTH Royal Institute of Technology de Estocolmo. Realizó su doctorado en la Universidad de Oxford, donde comenzó a trabajar con la misión ExoMars Trace Gas Orbiter para estudiar la composición de la atmósfera marciana, investigación por la que recibió el Keith Rankin Prize de la Royal Astronomical Society. Tras el doctorado trabajó en the Open University en el Reino Unido y en la Universidad de Tokio en Japón, donde continuó investigando la atmósfera marciana mediante el análisis de datos de distintos satélites y telescopios terrestres, además de participar en el diseño de instrumentación para futuras misiones espaciales. Actualmente trabaja en el Instituto de Astrofísica de Andalucía como investigador postdoctoral financiado por una beca a la Caixa Junior Leadership Fellowship. And today he'll talk to us about Mars atmospheric isotopes. So, Juan,
Okay. Well, hi everyone. Thanks very much for the introduction, Alvaro. As he said, I just recently started working here at IAA. I started in September, and we thought that it would be a nice idea for me to give a seminar so that people could get to know me a bit better and get to know what I do a bit better. And since I started my PhD, I started working with this mission, the ExoMars Trace Gas Orbiter, and in particular, I started focusing on, trying to understand the isotopic composition of the atmosphere, and that is what I will talk about today. Some of the investigations that I've been doing regarding the isotopes on Mars. So, okay, I'm doing something wrong, I think. And there we go. So I will start presenting introducing the Martian atmosphere and putting it a bit into context and explaining why I want to understand these isotopes in the atmosphere and why I believe that they are interesting. And hopefully after this talk, you will think that they are interesting too. Then I will be introducing the mission that I use to analyze these isotopes, which is called the ExoMars Trace Gas Orbiter. And then I will speak about the results and about the investigations that I've been doing with this mission. So let's start with the first part, the Martian atmosphere. I believe that in order to get a feeling of how the Martian atmosphere is and the main characteristics of the Martian atmosphere, it is good to put it into context with respect to the Earth. And in particular, when we compare the planetary parameters of both planets, there are some striking similarities, and probably Mars is one of the planets that most closely resembles our very own planet. In particular, when we look at the length of a day on Mars, it is about 24 hours as it is on Earth. When we look at the planetary obliquity, so the tilt of the rotation axis with respect to the ecliptic, it is very similar in both planets, which means that Mars experiences 4 seasons, as we do on Earth, and there's a summer season, winter, spring, autumn, and we actually see that the polar caps expand and shrink as these seasons occur. But as there are some similarities, there's also some differences. For example, the length of a year on Mars is about twice that on the Earth. The gravity is about 3 times smaller. And then the distance of the orbit with respect to the Sun, it is farther away. So Mars orbits the Sun at a mean distance of 1.5 astronomical units, which is larger than on the Earth, that is 1 astronomical unit. But then the eccentricity of the orbit, it is larger on Mars than it is on the Earth, which means that the relative distance when we are close to perihelion, that when Mars is closest to the Sun, and aphelion when Mars is at its farthest from the Sun, that relative distance is more pronounced on Mars. So the orbit is more elliptical on Mars than it is on the Earth. And as we will see later, what we see with the Trace Gas Orbiter is that this relative distance is actually a main driver of variations in the vertical structure of the atmosphere. But then, what about when we look at the atmosphere itself? Well, on the Earth, we've got an atmosphere with a surface pressure of 1 bar, filled mostly with nitrogen and with oxygen. However, on Mars, the atmosphere is a lot thinner. It's only 7 millibar, the surface pressure, which is mostly filled with carbon dioxide in 96%, followed by argon and nitrogen of around 2% each, and then some trace gases. And among these trace gases, we've got water vapor. However, it is important to note that under the present conditions of surface pressure and surface temperature, water can only exist as water vapor and as water ice, but it cannot exist as liquid water. However, has it always been like that? Well, there's numerous lines of evidence that suggest that this was not the case in the past, in which, well, these lines of evidence include the geomorphological evidence. That means that when we look with high resolution imagery at the surface of Mars, we observe surface features that resemble very much like the river valleys and the lake basins that, like the ones that we have on the Earth. And not only it is these surface features, but it is also the composition of the surface, and a number of the so-called aqueous materials, minerals have been detected, and these are minerals that form under the presence of liquid water. So these lines of evidence suggest that liquid water could be sustained on the surface in the past. However, if I'm saying that there's evidence for liquid water on early Mars, but currently the present conditions do not allow water to be sustained, does that mean that there was a transition in the climate from a warm and dense atmosphere that could sustain and could allow this liquid water to exist on Mars, and to the dry and thin atmosphere that we observe today? Well, one of the hypotheses is that at least a substantial fraction of the atmosphere has escaped to space. And this is supported by the isotopic evidence. So the isotopic evidence, well, what it says is that when we look at the heavy to light isotope ratios in the Martian atmosphere, the atmosphere is generally enriched in the heavy isotopes. So for example, when we look at the deuterium to hydrogen ratio in Martian water, it is about 5 times more enriched in deuterium with respect to the Earth. And not only that happens in deuterium, in water vapor, but it happens in other species, in argon, in carbon, nitrogen, oxygen. We observe that the atmosphere of Mars is generally enriched in the heavy isotopes. And well, it is believed that this is a proxy for atmospheric escape throughout history, because, well, when the atmosphere escapes to space, the lighter isotopes, they've got a lower mass, and therefore they can escape more easily, while the heavier isotopes tend to remain bound to the planet. And therefore, as escape occurs, the lighter isotopes can escape more easily, and that enriches the atmosphere in the heavy isotopes with time. And not only this isotopic evidence tells us that, atmospheric escape has occurred and has potentially been substantial, but also, if we couple these, if we quantify it and we couple it with evolution models, we can potentially reconstruct the density and the composition of the atmosphere of early Mars. However, making these reconstructions, typically you need information about 3 main things. The first thing is that you need information about the isotopic composition in the past, which is not easy to get. However, there's Martian meteorites that have arrived to the Earth, and they've been analyzed in the lab, and in some articles they provide estimates of what the isotopic composition of Mars was in the past. Then we've got the present, we need information about the present day isotopic ratios in the near surface atmosphere, because this is where the most of the atmospheric mass is, in the near surface. And these measurements are typically made by the rovers on the surface, for example, the Curiosity rover, or also by ground-based telescopes, because they are able to probe these lowest layers of the atmosphere. And then we need information about the so-called escape fractionation factor. That this escape fractionation factor, what it determines is how quickly the atmosphere gets enriched in the heavy isotopes as it escapes to space. Or in other words, it determines how much atmosphere must have been lost to space in order to reconcile the past and the present isotopic ratios. So this is a crucial factor that we need to estimate in order to reconstruct the escape history of the planet. And the way in which you calculate this escape fractionation factor is that you need to relate the isotopic ratios of the escaping species, so the escaping fluxes of, for example, deuterium and hydrogen, the heavy and the light isotopes, with respect to the isotopic ratios in the near surface atmosphere. And the idea is that not necessarily the isotopic ratios in the upper atmosphere where escape occurs and the isotopic ratios in the near surface atmosphere will be the same. And this is because there are a number of atmospheric processes that can alter the isotopic ratios. And this sets precisely the very main goal of my research. I want to understand what atmospheric processes can alter the isotopic ratios between the near surface atmosphere and the upper atmosphere. And if we want to study that, what we want to study is the fractionation as a function of altitude. And in order to make measurements and about that, the perfect mission is the ExoMars Trace Gas Orbiter. So this mission emerged as a collaboration between the European Space Agency and Roscosmos, and it was designed as a two-stage mission. First of all, in 2016, the ExoMars Trace Gas Orbiter and Schiaparelli were launched, and they arrived to the planet, to Mars, on the same year. Schiaparelli got released to the surface, and the Trace Gas Orbiter started an aerobraking phase until it reached its final orbit, that is a circular orbit at around 400 kilometers. And then we started science operations in March 2018. And then the second part of the mission, now it's in collaboration with NASA, that is the Rosalind Franklin rover that is scheduled for launch in 2028. And then what about the ExoMars Trace Gas Orbiter? Well, its payload comprises 4 instruments. So there's CASIS, which is a high-resolution stereo camera for taking images of the surface. Then there's FRED, which is a neutron spectrometer in order to measure the amount of hydrogen on the surface of the planet and the shallow subsurface. And then we've got NOMAD and ACS, the atmospheric chemistry suite, that are 2 suites of spectrometers, and suites meaning that each of them contain like 3 spectrometers within them, covering different spectral ranges. And ACS, which is the instrument that I use, that is the atmospheric chemistry suite, it has 3 channels, one for the near infrared, measuring between 0.7 and 1.7 microns, one for the middle infrared, measuring between 2.3 and 4.2 microns, and then TIRBIM, which stands for thermal infrared, is a Fourier transform spectrometer measuring between 2 and 17 microns. But the channel that I use is the middle infrared, and that is because it is a very high spectral resolution spectrometer, so it has a resolving power of 30,000, which is, I think, among the highest spectral resolutions that have been flown to space. But also in this spectral range, we've got absorption bands for a lot of gases, and also isotopes that are the bands that I actually study. And one of the main characteristics of this ExoMars Trace Gas Orbiter is the way in which it performs its observations. And these are the so-called solar occultation observations. So in order to illustrate how they work, I made a while ago like a small animation in order to see how they go. But basically here in the top panels, you've got some vertical profiles that I took from the Mars climate database, that they are vertical profiles, so at different altitudes. We've got the pressure, the temperature, the volume mixing ratios of carbon dioxide, that is mostly the whole atmosphere, and water vapor, which is a trace gas. And then we've got also dust in the atmosphere. So here you can see the vertical profiles for these. Here below, what you will be able to see is some model spectra at different altitudes as the video goes on. But the idea with these observations is that, well, here the blue dot represents the Trace Gas Orbiter, and what we do in these solar occultation observations is that we always point the instrument and it always looks towards the sun as we move along the orbit. Here the red dot represents the tangent point, and what you can see is that as we move along the orbit, the tangent point, the altitude of the tangent point starts decreasing. So in the very upper atmosphere, the atmosphere is very thin, and we just observe the solar spectrum. But as we start going down, we start observing the solar spectrum attenuated by the atmosphere. So we can derive a transmission spectra in which we can start seeing spectral features and absorption bands of different gases. In the upper altitudes, we typically observe absorption lines from carbon dioxide, but then as you start going to lower altitudes, you start observing the absorption lines of other gases, such as water vapor. And then when you hit the surface, the atmosphere is very dusty, which absorbs light at all wavelengths, and at some point it becomes so opaque that we cannot see light anymore, and we get a transmission of 0. But that's the idea in this observation. So, well, in this video, what I showed is how I modeled based on some vertical profiles in the atmosphere, how I modeled the spectrum, the spectra at different altitudes. However, what happens in reality and in our experiment is the opposite. What we observe is the transmission spectra, and then we use a retrieval engine in order to invert the spectra and reconstruct the vertical profiles. And these are the type of analysis that I've made. I've made retrievals in this transmission spectra in order to reconstruct the profiles in the atmosphere. And there are a number of reasons why the ExoMars Trace Gas Orbiter is particularly good at measuring trace gases. First of all, as it is shown here, if you look at the yellow line that represents the line of sight, here we are looking through the limb of the planet. And when you look through the limb of the planet, the amount of density that you see along your line of sight is much larger than if you look straight to the surface. It is about 30 times larger than if we look straight to the surface, which means that, well, we are maximizing our sensitivity to measuring potential gases that are found in lower abundances. Also, another reason is that, we are always pointing towards the sun, and the sun is a bright source of light, and that yields high signal-to-noise ratio measurements, which is also ideal if you are trying to look for tiny features in the spectra that with a lower SNR would be invisible, essentially. But well, these are the sort of observations that I use and that the ExoMars Trace Gas Orbiter does. So now I'm going to talk a bit about the results. And let's talk about the isotopic composition. And well, throughout several years, I've looked at the isotopic composition with these ExoMars Trace Gas Orbiter measurements of oxygen, carbon, and hydrogen in different species, in water vapor, in carbon dioxide, and in carbon monoxide. And what I think is quite neat is that, well, when looking at the isotopic composition of these different species, we have observed that they are fractionated or they are altered by different atmospheric processes. And actually, I think that it gives a pretty good overview of the sort of isotopic fractionation that you can have in planetary atmospheres in general. So even if it's not for the Martian atmosphere, this applies. These atmospheric processes fractionate the isotopes in all planetary atmospheres. So let's go through each of them in order to talk about these different processes. Let's start with the isotopic composition of water vapor. But in order to look at the isotopes, I think we first need to understand the variability of the water vapor abundance on Mars. In particular, what I'm showing in these plots, well, here you've got vertical profiles measured by the near-infrared channel of ACS from retrieved by Anna Fedorova in several papers. But here what you can see is, well, two columns. That the left column represents the observations in the northern hemisphere, and the right column represents the observations in the southern hemisphere. Then in each of these columns, the x-axis represents solar longitude, so this is time throughout the year or seasons. And then each of these rows represents different Martian years. And the colors here represent the water vapor abundance. And when I look at these plots, well, there are many ways in which you can analyze this data. But when I look at these plots, the most striking thing to me is the difference between the first and the second parts of the year. And that is driven mostly by the Sun-Mars distance, or at least to a large extent. So let's talk about that a bit more into detail. So here, well, what I'm showing is the same information now on the top panels here on the left. These are observations close to aphelion, so on the first part of the year, and then these are observations close to perihelion on the second half of the year. So during aphelion, what is it that we observe? Well, during aphelion, Mars is farther away from the sun, and it corresponds to the summer season in the northern hemisphere. And when we look at the water vapor abundance, we observe high values of the water vapor mixing ratio close to the surface. And this is because in the northern hemisphere, that here is represented by red, we've got the sublimation of water from the polar cap. So water vapor is sublimed, and it increases the amount of water vapor in the atmosphere, and that's why we observe high values of the water vapor mixing ratio in the northern hemisphere. But they quickly decrease with altitude above 10 kilometers. And this is because we've got the formation of water ice clouds. that essentially condense the water, and they make the volume mixing ratio in the atmosphere to decrease. And what is it that we observe for the southern hemisphere? So the blue lines here in the close to aphelion. So where it is now the winter hemisphere. Well, since it's winter, the atmospheric temperatures are very cold and the water condenses into the polar caps. And that's why we observe very low abundances of water vapor. And this is rather different if we compare these two plots. The water vapor distribution between these two parts of the year is very different. Now, during perihelion, so when Mars is closer to the Sun, it receives more solar insolation because it's closer, but also the atmosphere is dustier, which increase the dust, the heating rates in the middle atmosphere, and it prevents the condensation of water vapor. And therefore, water vapor is allowed to extend to much higher altitudes. So we find condensation, but instead of happening closer to the surface at 10, 20 kilometers, it happens at much higher altitudes, around 50 kilometers. And that's why the water vapor abundances in the southern hemisphere, where it's the summer season now, they are largest, but they can extend up to high altitudes, and then they decrease. And not only we can observe these high values of the water vapor abundance in the southern hemisphere, where it's summer, but also in the winter hemisphere. And it is because these increased temperatures, they increase the atmospheric circulation, and water is enabled to be transported from the southern to the northern hemisphere, even though it's the winter hemisphere. And that's why we also observe high values of the water vapor abundance in northern hemisphere. But then this is about the water vapor abundance in general. What is it that we observe for the isotopes? Well, in principle, H2O and HDO are very similar molecules. They are different isotopes, but chemically they behave the same and they undergo the same processes. The thing is that, if that was the case, we would expect their ratio to be constant all throughout the year. But when we look at the measurements, what we observe is that now, again, for the first half and the second half of the years, is that the shape of the profiles resembles very much the shape of the profiles of the water vapor abundance. And this is because, indeed, HDO and H2O behave differently. In particular, the saturation vapor pressure of H2O and HDO is different, and HDO condenses a bit more efficiently than H2O. Therefore, when the water ice clouds form, HDO condenses more efficiently, so it depletes the atmosphere in HDO, which produces a depletion of the D/H ratio. And that is what we observe in the profiles, and that's why we see that they are tightly correlated. So during the first half of the year, when we had water ice clouds being formed at around 10, 20 kilometers, we see a sharp decrease of the D/H ratio with altitude. However, in the second half of the year, when we had these water vapor abundances extending up to high altitudes and then condensing, that's what we observe. We observe high values of the D/H ratio and then decreasing because of this preferential condensation of HDO. And if we want to test whether this is indeed what we are observing, what we can do is to use a Mars general circulation model that is called the Mars Planetary Climate Model, and which is rather sophisticated, and it has a water cycle including many processes, but also it treats HDO and H2O independently. So you can include the different condensation rates for HDO and H2O, and this is what is known as the condensation-induced fractionation effect. And when you include these independent condensation rates or saturation vapor pressures for HDO and H2O, this is what the results look like. And essentially, the variations that we can observe in the GCM, they resemble very much what we observe in the ACS profiles. And therefore, we can conclude that in the case of water vapor, it is the condensation of water into water ice clouds that produces the fractionation of the isotopes with altitude. Then what happens when we look at the isotopic composition of carbon dioxide? In order to introduce that and to show the results, I would like to first introduce the concept of homopause. So the homopause is a sort of imaginary boundary that essentially defines the boundary between two mixing regimes. So below the homopause, we've got the so-called homosphere, in which we've got efficient turbulent mixing from the atmosphere. And this turbulence tends to mix the gases and to keep the atmosphere well mixed, which means that the volume mixing ratio of the gases remains constant with altitude, at least species that are chemically long-lived, and they are constant with altitude, their mixing ratios. And well, the density of all